Good morning, students. Yesterday we have completed Kepler's laws. Kepler given these laws depending on the regular observations that I have told you yesterday, positions of the planets by regular observation. But he couldn't have any explanation why these planets follow these laws. But these laws help Newton to give his theory of gravitation. In the very beginning, we have seen how how Newton thought about the gravitation. He was sitting under the tree, then apple fell down, etc. And he thought that there must be attraction between or Earth is attracting the apple towards itself. But gravitation is not that much sufficient, or that much is not included in the gravitation. He has given the universal law of gravitation. According to his law, suppose I am having these two objects. These are having different masses. And what Newton told, there is attraction between the two objects in the universe. This is the universal law of gravitation. There is attraction between the two objects in the universe, and this force of attraction is directly proportional to the distance between the product of the distance is directly proportional to the product of the masses of the two objects and inversely proportional to the square of its distance or square of distance between them. Suppose I have given you here the two objects, that is they are having mass m1 and m2. So the force of attraction is there between them, that is they are attracted towards each other, and distance between them is d, means that distance is taken from the center of this. Suppose this object is circular object or spherical object, we can say. But if the objects are not spherical, then what the distance is taken in between them? That distance is taken between the center of their masses of the two objects. That distance is considered. Here these objects are spherical objects. The masses of these objects are m1 and m2. The distance between the two is d. So what law says? Universal law of gravitation. There is force of attraction between the two objects in the universe. That force is directly proportional to the product of the masses of the two objects and inversely proportional to the square of the distance between them. That is the law of gravitation. This law is also asked in the examination. Now he has given mathematically this equation, that force is directly proportional to the product of the masses m1 and m2, and inversely proportional to the square of the distance between the two objects. Now we know, last year we have studied that if you want to remove the proportionality sign, we have to consider one constant. That constant is here g. F is equal to g m1 m2 divided by d square. We have removed the proportionality sign and we have taken the proportionality constant. Proportionality constant is here g. So F is equal to, force is equal to g into m1 m2 divided by d square, where g is the constant of proportionality. Just I have told you, constant of proportionality, and it is called the universal gravitational constant. Now hereafter you have to remember, capital G is called the universal gravitational constant. We have to consider in solving the numericals also, its value, etc. that we have to remember. Now according to this law, if we double the mass of one of the objects, now it is in the numerator, so force is also doubled, that we can calculate. If mass of one object is doubled, the force is also doubled, because in the numerator it is, so it is also doubled. But if the distance between the two objects doubled, then the value of F is decreasing by the factor of 4, because it is in the denominator. This also can be asked for what? Fill in the blanks or multiple choice questions. if the distance between them is doubled, then the force decreases by the factor of 4 because it is in the denominator. Now, Henry Cavendish has first calculated the value of G. G is equal to, now what we have to do here, F is equal to G m1 m2 upon d square. Then if we want to calculate G, as we know mathematically, this will come to this side and m1 m2 to the denominator. Now accordingly, G is equal to n F into d square upon m1 m2. If we want to know the unit of G, then, or SI unit of G you can say, so force is measured in terms of Newton. Distance square is there. So we have to take m square. Distance is measured in terms of meter. So meter square, and masses are measured in terms of kilogram. So it is kilogram square. So Newton meter square per kilogram square is the SI unit of universal gravitational constant, or it can be written in this way also, Newton meter square per kilogram square, or it can be written in this way also, Newton meter square. We have to read in the same way, per kilogram square, that is the SI unit of G, or universal gravitational constant, or CGS unit you can calculate, or you can write accordingly, dyne centimeter square per gram square, but it is given in, that is SI unit, Newton meter square per kilogram square. So Henry Cavendish was the first scientist who measured the value of G experimentally, and that comes to be 6.673 into 10 to the power 11 Newton meter square per kilogram square. This value, Newton meter square per kilogram square. We have to remember this value also for solving the numericals. So value of G is equal to 6.673 into 10 to the power minus 11 Newton meter square per kilogram square. That value is constant, that is universal gravitational constant. We have to remember this value for solving the numericals. Now next point is uniform circular motion or magnitude of centripetal force. Yesterday we have seen what is the centripetal force, that is the center seeking force. Or in the uniform circle, whenever we say that an object is moving in a circular motion, or that uniform circular motion, then that object is acted upon by the what? The centripetal force. Last year we have studied Newton's laws of motion, Newton's laws of gravitation, etc. Newton's laws of motion, Newton's equations of motion, etc. We have also studied speed is equal to distance travelled upon time, velocity is equal to displacement upon time. That all these things we have studied last year. Now an object moving in a circle with constant speed, that we have studied, is acted upon by a force directed towards the center of the circle, and that force is called the centripetal force. That we have studied the experiment of string. That string is moving continuously in the circular manner. Whenever we hold it, then and then only it will move. If we release that force, then it will fall out. So that force is called the centripetal force, that is towards the center seeking force. Now these are the, now we know very well, m is the mass of the object, v is the speed of the object or velocity of the object, r is the radius of a circle. Then it can be shown that F is equal to mv square upon r. Now we have to consider this regarding the planet and the sun, that we have studied yesterday. The planet is revolving around the sun in an elliptical orbit. So similarly, centripetal force acting on the planet towards the sun means all these planets, they are revolving around the sun due to the centripetal force, must be F is equal to mv square upon r. Now again here m is the mass. Now here we have to consider m is the mass of the planet. We cannot say object, but m is the mass of the planet, v is its speed, and with which speed it is revolving around the sun, and r is its distance from the sun in this way. So mass of the planet, then speed of the planet, and the distance from the sun. So the speed of the planet can be expressed in terms of the period of revolution. Yesterday we have seen t square is equal to is directly proportional to r cube. So the distance traveled by the planet in one revolution. So object is moving in the circular manner that we know, or planet is moving around the sun in the elliptical orbit or the circular orbit, we can say. So that distance is equal to the perimeter, or we can say circumference of the circle, that is the distance covered by the planet, that is equal to 2 pi r, that is the circumference of the circle. So that is the speed or velocity is distance traveled divided by time taken. So 2 pi r, distance traveled is 2 pi r. In one revolution it completes, it covers this much distance equal to that of the circumference divided by the time, that is time taken for one revolution. Now F is equal to, if mv square upon r, then we have to put this value of v. V is equal to 2 pi r upon t. So m as it is, v is 2 pi r upon t whole square, that is mv square it is, and divided by r. It comes to be m here as it is 2 square 4, then 4m pi square r square divided by t square, and divided by again r. So I have written in this way 1 by r. That comes to be 4m pi square r, because 1 r and 1 r here getting as r square means r into r divided by r, 1 r getting cancelled. So 4m pi square r divided by t square, multiplying and dividing by r square, we have to divide and multiply by r square. So this is F is equal to 4m pi square r divided by t square. We have to multiply and divide it by r square. Then we get, see, F is equal to 4m pi square r divided by t square into r square, multiply by r square and divide by r square. Then 4m pi square r into r square, that is equal to r cube. Then t square and multiplied by r square. Now 4m pi square r square I have written in this way, and r cube divided by t square I have written in this way, r cube divided by t square. We have seen yesterday Kepler's third law, that in that we have considered t square upon r cube is equal to k. But what we have got here r cube upon t square means inverse of that. As t square upon r cube is equal to k, then r cube upon t square is equal to 1 upon k. So I have written in this way. So F is equal to 4m pi square r square into 1 upon k. 4m pi square upon k, only rearrangement, into 1 upon r square. Now this total value is constant. How it is constant? K is constant, that we know. Mass of the planet is constant, it is not changing. Value of pi is also constant. So this total amount is constant. So F is equal to 4m pi square upon k into 1 upon r square. And we know very well, if we want to remove the proportionality sign, we take the constant. And if I want to remove this constant, I have to take the proportionality sign. So F is directly proportional to the distance of the planet from the, F is inversely proportional to the square of the distance of the planet from the sun. Now this was given by Newton. This force is inversely proportional to the square of the distance from the sun, and this force Newton identified as the gravitational force. But he knew that, or this force is in the universe, this force is very much weaker, but it is very much important for the revolution of planets, etc. And it is possible due to the huge masses of the planets, stars, etc. In this way, Newton considered this is the centripetal force or the gravitational force, which is inversely proportional to the square of the distance of the planet from the sun, and this he identified as the gravitational force. Now we know that I have told you, according to universal law of gravitation, there is attraction between the two objects in the universe, and that force of attraction is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. Again, I have told you just now, these two objects are there, there is attraction between them. You are sitting on the benches, 2 or 3 students, they are sitting on the benches and they are also attracting each other. Then you will ask that, madam, so why we are not attracted towards each other? This force of attraction, I have told you, very much weaker. And how much weaker it is, that we will consider one numerical example tomorrow, and then you will understand that there is force of attraction, but that force is negligible, so we are not attracted towards each other. We will see tomorrow.